Oh, I see everybody in my lab now. Saw your parents the other night. I was griping. Did they talk about me griping about the headmaster?
They did not.
Oh, good. I thought I'd made enemies. All right, so it's a pleasure to have Gabe Loewinger here. Gabe did his undergraduate degree at Pitzer College, which is part of the, what do you call it? Claremont College's Consortium. Scripps, Pomona, Harvey Mudd, Claremont, McKenna, and Pitzer. Wow. Okay. Some of my favorite neuroscientists went to Pomona. He is I think you've already received your master's degree from Harvard in biostatistics, worked in several leading neuroscience labs in the area of neuromodulation and addiction. So he shares an overlapping interest with that, but he's a biostatistics PhD candidate at Harvard School of Public Health. I'll let him tell you what his interest will be. But he has been doing some work with Ken Kashida, and so it's cool to have everybody, all these past colleagues here, Sam McClure and Ken Kashida here. So he's got a small but potent audience to sort of pick at him, plus my folks. What we're interested in doing is getting Gabe, sustaining Gabe's interest in neuromodulation, because we think we have some methods that are going to spread out, and so sort of proselytizing is part of our work. So with that, no further ado, just so you'll know, this is being streamed and it'll be archived on our YouTube channel and other gettable places. So be careful about scratching your face and things like that. So anyway, welcome to Virginia Tech. It's good to have you.
Thanks, Dr. Montague. Thanks, everybody, for coming. So before I get started, a big thank you to Dr. Ken Kashida, Dr. Reed Montague for having me down, and Christine for helping organize everything. So as Dr. Montague mentioned, I began doing research in neuroscience labs and was doing a lot of work with cyclic voltammetry in rodents. And right around the time I was starting to apply to grad school, I learned about the work that Dr. Montague and Kashida were doing, and I thought the voltammetry work was really, really innovative, and I reached out. And so when I began starting my doctoral thesis research, I became a part of a group that was, in a funny way, doing statistical methods that had a lot of overlap. And so Dr. Kashida and I started a collaboration trying to generalize some of the what I thought was really innovative applications of machine learning to neurochemical sensing. So I'll start out with chatting a little bit about cyclic voltammetry, trying to provide a little bit of motivation for the statistical methods I'll be showing. And I'll introduce the experimental methods that we employed to generate the data that Ken and I have been working with. Tell you a little bit about how we validated statistically the methods that we'll be looking at. And then I want to spend a little time introducing ensembles. I know a lot of people here have probably worked with them before, but just to get a little bit of intuition for the building blocks of what I'll be talking about. And then I'll show you the results from kind of standard methods, standard statistical methods, and also the work that I've been developing. I'll be showing both data from a couple different kind of pre-processing steps that people are familiar with these techniques know about. And at the end, I'll chat a little bit about stuff I've really recently been doing, trying to build upon these statistical methods with combinatorial optimization. So we'll start out here. I think a lot of people in the audience know a lot more about this stuff than I do, but in the spirit of giving a little bit of scientific motivation for the statistical methods, dopamine's role in cognitive functioning has received a lot of attention in the literature over the past 3, 4, or 5 decades, and in particular interest has focused on its role in disease states as well as learning and memory. In particular, coming from the cyclic voltammetry world, a lot of stuff I've focused on is mesolimbic dopaminergic pathways that have been involved in reward learning, and a lot of focus has been on its role in drug addiction. Again, I know there's a lot of work here that's being done on this, and I think a lot of people here can speak a lot more to this than I can, but broadly speaking, mesolimbic dopamine release, in particular mesolimbic dopamine transients, so rapid shifts in dopamine concentration, have received a lot of attention for their role in reward learning. And people have posited a number of different theories about how it contributes to reward learning, prediction error, kind of factual prediction error, incentive salience. But a lot of the work is focused on these dopamine transients, these rapid shifts in dopamine concentration. And so as a result, people in the field have had a lot of interest in techniques that have high temporal resolution that can capture some of these rapid shifts. And I have some images from kind of the historically classical voltammetry world. And I thought I would start off by just kind of saying a couple words about the kind of conventional historical narrative about cyclic voltammetry. So the technique works, as some of you may know, it's an electrochemical technique, works by rapidly varying voltage potentials between voltage limits. And historically, the idea was that between these voltage, these kind of set limit points, dopamine would oxidize and reduce, and the voltage potentials at which these redox reactions occurred would allow for the not only the identification of the presence of dopamine at the surface of the electrode, but also quantitatively allow for estimation of concentration. I think Dr. Montague and Dr. Kishida have done really innovative work kind of building upon this, and I've suggested that the picture may not be entirely complete with the classic narrative, but the idea is that by varying voltage and measuring current, we can estimate the concentration of neurotransmitters with very high temporal resolution. But as I just mentioned, we're not cyclic voltammetry doesn't directly measure the concentration of neurotransmitters. We're measuring current, we're measuring electrical activity, and so this requires a statistical step, where we take the data, the electrical data that we record, and we convert it somehow into estimates of neurotransmitter concentration. So this step is really what I'll be focusing my talk on today. And this is the kind of statistical methods that got me interested. And so the idea is that one somehow needs to generate a training set for a statistical model. And oftentimes this is done in vitro, frequently in flow cells, where the investigator knows the concentration of neurotransmitters that they're interested in, and through exposing voltammetry electrodes to varying known concentrations of these neurotransmitters, we can train, we can generate in vitro training sets that we can then use to train statistical models. And with those statistical models, we can take the in vivo data that we're really interested in scientifically, apply these models, and use them to estimate the concentration of neurotransmitters to address some of the scientific questions of interest. This step is what I'll be focusing on, and specifically, how we can improve upon the predictive performance of these statistical models. And specifically, as I said in the title of the talk, I'm interested in kind of the generalizability of these statistical models. So it's probably pretty intuitive that the in vivo environment in which we're actually collecting the data in the experiments we're really interested in differs substantially from the environment in which we're generating training sets. And moreover, the electrodes in practice that are used to generate training sets it's not always feasible to use the same ones for generating the training sets as we would use for collecting data. So there's a kind of a couple motivations for why we'd be interested in trying to improve upon the generalizability of the predictive performance of these statistical models that we use to convert the raw cyclic voltammetry data into concentration estimates. So in an attempt to kind of get at this idea of cross-electrode generalizability, the work that I'm going to be presenting on today is a very simplified version of it, which is that if we have some collection of in vitro training sets, where each in vitro training set was generated on a different electrode, can we somehow aggregate information across a subset of those electrodes and make predictions on other electrodes that were not used to train the model? and see if we can improve the predictive performance of this. So that's what I'll be focusing on for the talk. To sort of drive home, at least in the electrodes that I have, and I'll speak to that in a second. These are carbon fiber microelectrodes used that were made to be chronically implanted in the striatum of mice. There's a lot of between electrode variability. Here here's just a random subsample of average cyclic voltammograms or average CVs of 4 different electrodes of data that was generated in Dr. Ken Kishida's lab. So, it may be intuitive just kind of looking qualitatively at this that a statistical model trained on electrode 1 may not perform very well in making predictions on data collected in electrode 15, let's say. So let's move into the data that we generated and the statistical validation scheme. So the data were generated as follows. I got 15 carbon fiber microelectrodes, as I mentioned, from Dr. Joe Cheer's lab at the University of Maryland. And in Dr. Ken Kishida's lab, we took these 15 electrodes, and for each electrode, we put them in a flow cell, and we exposed the electrode to varying concentrations of dopamine at varying pHs. And there was about 30 concentrations per electrode, and at each concentration, we took, after kind of processing the data carefully, about 700 observations per concentration. So the data frame looks as follows. This is kind of what I'm working with statistically. We have an outcome vector, which is dopamine. This is just concentration, a strictly non-negative outcome variable. And so at each concentration, we are measuring 1,000 discrete voltage potentials. Or I should say we're measuring the current at 1,000 discrete voltage potentials. So our kind of covariates or our features for each observation is in the 1,000 by 1 vector. It's these 1,000 currents measured at these 1,000 discrete voltage potentials. And for each concentration, we have about 700 replicates. And then we have 15 of these kind of data sets. So how did I validate it? These things that kind of look like popsicles are supposed to be electrodes. So we start with 15 electrodes. And for each electrode, what we do is we take 14 of them. We hold out one of them as a validation electrode. We somehow aggregate information across here. Oh, there we go. We somehow aggregate information across these, train a model, and we make predictions on this validation electrode where we know the truth. And so we cycle through. So now we've held out, electrode 14, and we have the rest of them all the way down to electrode 1, held out. And for each one, we get an average prediction error. How far off from the truth were we when we trained up a statistical model, made predictions based upon the voltammetry recordings in the held out electrode, and then compared to the truth. So as I mentioned, from my understanding, working with Dr. Kishida, it's common to use the derivative, a numerical estimate of the derivative of the cyclic voltammogram as the covariates or the features in the model training. So I'm going to show both of I'll show my methods in both the raw CV and in the derivative of the cyclic voltammogram. So I'm going to start out with the raw data. So I did want to make one very brief point about kind of modeling schemes. When I first got the data from Dr. Ken, yeah, sure, please. This variability, I think, comes from the electrodes themselves. Yeah, great question. So when I received the data from Dr. Ken Kishida, I spent a while experimenting with different modeling schemes and kind of went about tuning hyperparameters all the same way and just trying to see with the data at hand what worked the best. And historically, principal component regression, although applied in a fairly different manner, was very common in the field. I know among Dr. Montague and Kishida's lab, the elastic net and lasso, these regularization methods are also common. The data that I had when I applied it ended up, the best predicted performance came from principal component regression, where we tuned the number of components used in the exact same way one would kind of tune hyperparameters if you were doing a regularization method. But that being said, all the methods that I'm talking about today are completely independent of this step. There's nothing about the statistical methods I'm working on that are specific to any kind of model fitting scheme. And so if one had reason to believe that a different method was superior, there's no reason why you couldn't use the. So I thought I'd start off with just a little bit of intuition about ensembling methods. I imagine some people here are familiar with it. But just to get a little intuition for kind of the backbone of the talk, here's a slide from a story I heard on NPR some 4 or 5 years back. And it's not about ensembling itself, but I thought provided nice intuition for the kind of statistical concept behind it. So it's the story on NPR was motivated by a book that was fairly famous, I think written some 10, 15 years ago now by James Sawicki, he's like a New Yorker reporter. He wrote a book about how the wisdom of crowds, so basically the kind of aggregating information across large groups of people often, or like collective wisdom often far outdoes that in terms of decision making of individuals. So if you were to compare, the wisdom of a crowd versus a smaller group of experts, the crowds would on average perform better. And so he uses this kind of notion, this heuristic, to describe how things like the stock market functions. And so he opens with a nice kind of story about Francis Galton some 150 years back at a county fair. And the story is that Francis Galton went and there was some kind of game where they put up an ox on stage and they asked everyone to guess the weight of the ox. And Francis Galton, being the kind of scientist and statistician that he was, guessed that if he were to take everybody's guess in the room, there'd be some people who had no idea what they were talking about and would guess 3 pounds, and there'd be other people saying 50 tons. But then on average, if you just averaged across everyone, it would tend to do much, much better than anyone who let's say, worked with oxes or had experience from them. In the end, the story goes is that when he did in fact average everyone's guesses, it was only 1 pound off from the true ox weight. So it's not very believable, but NPR was kind of fascinated by this, and they thought they would give it a shot, and so they took a picture of, here's Penelope the cow, they put it online, they asked people to guess the weight of the cow, and then they averaged across everybody, and they found that among some 17,000 respondents, they were within like 3 or 4% of the true cow's weight. And they asked people to self-report whether they were cow experts. I'm not really sure what that means, but they reported that they knew a lot about cows, and among them, it was a subset of this 17,000. There was about 3,000 of them, and they did slightly worse. So anyway, with this kind of heuristic in mind, the intuition I think it provides for ensembling is that of the wisdom of the crowds. That one might begin with multiple data sets or begin with a larger bunch of data sets and kind of cut them up in some way. And for each subset, train an individual statistical model and use each of these little models to make predictions and then somehow aggregate across the predictions. And that this step often produces, although not always, improvements in predictive performance. Here, just a really quick kind of toy example, just to build a little bit more intuition. Here's a toy data set I simulated. We have some predictor X, some outcome Y, and here's 100 data sets, and I fit a best fit line, so there's just a linear regression. Let's say I wanted to make predictions on X equals 75. The predicted value is going to be here, right where the dotted line intersects the blue line, and we get a predicted value of about 78, 79. Let's say I just took a subset of the data and fit a linear regression on it. Here's just a random subset, these highlighted red dots, and we might end up with, in this case, we end up with a fairly different prediction. Let's say I did this many times, or 4 times, where I kind of split up my original data set into four roughly evenly sized subsets of the data. and I fit 4 different regressions. Each of them might have different predicted values, and then I can take the mean across each of these different models' predictions, and now I have an ensemble mean, an ensemble prediction. So that's just the basic intuition behind ensembling. It's simple, yet in some cases really, really powerful. As this is a method that in my group back in Boston, my boss is very into ensembling in settings where you have many, many data sets and you're trying to aggregate information across them. And we have both some theoretical work and some empirical work in data sets and simulations that supports the idea of ensembling in certain settings. So kind of first crack at dealing with the data that I told you about is what I just call a naive ensemble, which is for each electrode, we have a data set, right? And for each data set, we fit a single model. So we do that for each of the kind of training electrodes, right? And with each of them, we make predictions based upon the recordings from the validation electrode. And then we're just taking an average of these. So we're just ensembling the predictions at this really basic level, where there's an individual model for each of the data sets generated from each of the electrodes. Formally, this is saying exactly what I just said, and I'll show you first just the results from the raw. It ends up doing very, very poorly, as we'll see in a second. The first method that I worked on over the past year was something I call covariate profile similarity weighting, and it's a simple idea, which is that predictions made from models that were trained on electrodes that are more similar to the electrode that we're making predictions on is going to be a better source of predictions, right? So let's say, for example, that I have the red electrode here is the test electrode. And the blue one here is just one of the training electrodes that I have, right? One way of kind of thinking about the similarity between these electrodes is just looking at their inflection points. And specifically, the distance between their inflection points, right? If they're really similar, this distance is going to be small. If they're very different, the distance is going to be large. And so I use this as this was kind of just a home-cooked dimension reduction method that my boss suggested to me a while back. And it ended up being useful, and so we stuck with it. It's just the squared L2 norm of the difference in the vector of the coordinates of these inflection points. And just intuitively, it's just the squared. Just if you took a ruler and just squared all of these and added them together, that would be your similarity measure. So the algorithm is as follows. We do exactly what we said before, right? We take each electrode, we fit a model, we make predictions on the target, and for each electrode, we identify these inflection points and we calculate the similarity between them, and we weight based upon this similarity measure. So we just take a weighted average. So, right? So if we had, let's say electrode 1 was kind of this far away, this would be down-weighted relative to electrode 2, which is very close by. This is formally the way that we construct the weights. It's just standardized, so they sum to 1. And this produces a big reduction or a large improvement in predictive performance. The next idea that I developed with my group is something I've just called the study strap, named after the bootstrap. And the idea here is to generate a lot of fake electrode data sets. Generate a lot of fake electrode data sets. So if anyone's familiar with bagging, this is kind of like bagging at the level of the study or the level of the electrode. Generate fake studies for each kind of fake pseudo-study replicate, pseudo-electrode replicate, train a model and make predictions and just average across them. So we're just ensembling across models trained on these fake electrodes. So the algorithm is as follows. So let's say let's just take a really simple case where we have 10 electrodes, 10 training electrodes, and each electrode has 1,000 observations, and we want to make a fake electrode that's 1,000 observations. So what do? We're going to take the numbers 1 through 10. We're going to randomly sample with replacement, and we're going to use this random sample to determine the proportions of observations that will subsample from each of the training electrodes. So then here, so we got 2 2s, a 3, 3 5s. We'll calculate the number of observations, the proportions to subsample from each of the electrodes. Then with these proportions, we'll take we'll take a corresponding random sample from each of the electrodes. So here, just the color here indicates which electrode it was sampled from. In these, we'll sample randomly within these proportions, right? So now this is my new fake data set, my new fake electrode. And then I fit a model on each of these, and I make predictions and I average across them. Just a teeny bit more to build intuition. Let's say I had gotten 1, 2, 3, 4, 5, 6, all the way up to 10. So I'm going to be sampling 100 rows from each of the studies. Let's say I gotten 2 2s, a 3, 3 5s, like from before. We're going to end up with that, a corresponding proportion from each electrode. So this does quite a bit better than the other guys. All right, so the next idea is just applying that covariate profile similarity weighting, right? Giving more weight to electrodes that are more similar, but now we're just doing it with the fake electrodes. So the algorithm is the same as before up here, right? We're generating these fake electrodes, and now I'm taking the average across all of these. I'm saying how similar is it to the electrode we want to make predictions on, calculate this distance, make predictions, and then take a weighted average of the predictions across all of the different fake electrodes that I've generated. Again, it's the same heuristic. We're downweighting ones that are more different. If these are my study straps, my fake electrodes, and then we're upweighting those that are more similar. The weights are defined just as before. And this does very, very slightly better, but nothing to write home about. Please.
You said that one of the reasons you want to do this is because you can't always use a flow set. You can't always test your electrodes in a flow cell.
Sure.
So, but the similarity metric sort of requires that you know how it will respond in this controlled environment.
I think
You need the rate curve, which is what you get from the flow cell for the electrode of interest. So how would you, in practice, get this similarity measure if you don't have it tested in the flow cell? You don't have it in the data set.
Yeah, no, that's a great question. So I guess the idea is that even in Vivo, we would have a background CV. We would have a cyclic voltammogram. We would get to observe the design matrix. So it may be noisy, but we would we're looking at averages here, so we would average across it. And so we can still get a measure of similarity in the average features between the training electrodes and the one we're measuring in Vivo. Granted, the one that's in Vivo might be a little noisier. All right, so does that answer your question?
Kind of. I mean, so you do the voltage sweep in Vivo.
Uh-huh.
You don't know what the dopamine concentration is, right? So that column in your
Right.
data frame isn't filled.
Right.
But I guess if you do that sweep, then you get some curve, and you can still sort of say how close. So it's going to be met. No, that's what you mean by noisier. It's going to approximate one of your training curves.
Yeah, exactly. I mean, the similarity measure is basically, it's not basically, it is measuring the similarity in the features, the covariates. So we don't need, there's nothing about this that says, oh, we need to know the labels, the dopamine concentrations. What it's saying is, let's take more seriously the models that are trained on electrodes that are more similar. So if we're implementing the technique in Vivo, we'll still get a CV. We'll still get these covariates. It would be as far as I understand, and feel free to chime in, it would be the exact same process since we're still going to have the design matrix. Okay, so the last method that I've worked on, I just call the covariate match study strap, and it's a similar idea to what I just showed, but we're just embedding an accept-reject step. So the idea is as follows. We generate one of these pseudo-electrode replicates, pseudo-study replicates, and we're estimating the similarity metric. And then we're fitting, the first time around, go ahead and fit a model. Fit a model based on this fake electrode. And then take the inflection points and a similarity metric, right? So the distance between that fake electrode and the electrode we want to make predictions on. And set a threshold and say, everybody who comes after me has to be at least as good as me if they want to be in the club. Everyone else, throw away their data. We're not training any models on it. So then each subsequent time, we have this accept reject step where we say, okay, show me the fake electrode that was randomly generated. Are you as similar as the guy before you who we accepted? If you are, take the data, train a model, and update that threshold. And we'll get increasingly closer to, at least in the covariate profile, the CV, to that of the accept reject step. Of the test electrode. So this one does the best, and I'll kind of zoom in a second. So I'll just show this little graphic just to get a little intuition. So let's say the red electrode, this is the algorithm working. Let's say the red electrode is the test electrode. What I'll show you in a second is the accept reject algorithm working in real time, where each blue curve is the average CV of the fake electrodes that were accepted. And I'll show dotted lines indicating some subset of the rejected electrodes, the guys who we don't accept, we don't train any models on. So hopefully this will be visible. So you can see the blue line, it's fairly close, and this is just some subset of ones that were rejected. Now we've accepted a couple more, and so it kind of randomly, it iterates until some convergence criteria. And convergence criteria, I just make it go a long time without accepting. So perhaps the simplest method of all which is just a standard method, and it does shockingly well in this setting, and that's just merging. That's just taking a whole bunch of electrodes, throwing them all into one data frame, fitting a single model, and making predictions. So in this case, it actually does on par with some of the other methods that I developed. It's not as good as the one I just showed you, the accept reject step, covariate match study strap, but it still does very, very well. Okay, so at least on the raw data, we see as we'll see in a second, we see much better gains than in the derivative. But here we're getting about a 13.5% reduction in prediction error, comparing this accept reject step method to just the merged, which is like a kind of the standard method to beat in this case, since the naive ensemble, as we saw before, was so horrible. Okay, so let's look at the derivative. I am just going to kind of show all the results at once since we've gone through how they work. Right, so again, here's some subset of electrodes, and here's their corresponding numerical estimate of the derivative of the CVs. So the idea behind the derivative is that we still have this, for each of the data sets, we still have the exact same concentrations. What we're doing is we're taking a numerical estimate of the derivative of the covariates, or of the features, so of the cyclic voltammograms themselves. So before I go into this, I just wanted to talk very briefly about one element of the statistical methods I'm working on, which is a parameter that I kind of glossed over when I introduced this, and that's like what we call a bag size. So as I mentioned before, in this toy example that I offered just for intuition, where we have 10 electrodes, 10 training electrodes, and we want to make a fake electrode that's 1,000 observations long. We have a bag size of 10, meaning I'm taking a sample of length 10, a vector of length 10, randomly to determine the electrodes that are represented in my pseudo-study replicate. So let's say I change that to 5. What's that going to mean? It means there's fewer possible electrodes represented in this fake study, right? And then once they are represented, the kind of proportions of observations that we're subsampling from each of these studies is all still less granular, right? So it could be, if we were to sample electrodes 2, 3, 5, and 8, we're going to be taking a fifth from each of these. Similarly, if we had sampled 1, 1, 3, 3, 3, we're going to be taking 2 fifths, 3 fifths. So here's a bag size tuning curve, and it turns out if you do the derivative, if you look at the raw data as we saw before, the optimal bag size is right around the right around the number of training electrodes that we used. We kind of get this dip here. It shoots up here, so we can't see it. And then for the derivative, we see the kind of optimal level is way further out. Without kind of getting too much into it, for me, this is suggestive of the derivative providing some sort of standardization. So what does it mean for the bag size to be 75? Well, it means that there's a greater number of kind of possible electrodes that can be represented. And when the bag size is this large, it's also much more likely that every electrode is going to be represented in this fake electrode, or this pseudo-study replicate. And also the granularity with which we're subsampling from each of the electrodes is going to be finer, right? So we're going to be getting numbers like 120, 53, 13. If we're looking at a bag size of 75, whereas when we're looking at a bag size of 10, right, we're going to be in steps of 1/10, 2/10, 3/10. Okay, so I used that, I tuned that curve, and then I applied the methods I told you about before. The story is similar here, but what we get is a big improvement actually in the merged. This kind of very standard method of just kind of throwing it all into one bag, and so the gains we get are far more modest on the derivative. We're getting a 3.5%, 4% improvement. So I just wanted to throw this up really quickly just to kind of justify my choice of the PCR. When I experimented around with this, I often found that when I experimented around with the kind of regularization methods, I often found that the elastic net was pushing me towards the lasso. And so here I've just shown tuning the principal component regression and the lasso in an identical fashion. I found that, at least in my data set, the principal component regression, both on the raw and the derivative, tended to exhibit superior predictive performance. But certainly is not bad, and I can imagine that this might shift from data set to data set. Okay, so I just wanted to speak very briefly to some work I've been doing more recently on combinatorial optimization methods to kind of build upon this framework that I've introduced. So combinatorial optimization, or integer programming as it's sometimes called, is a really useful method in this setting because it allows, the reason I implemented it was because it allowed us to bypass the accept-reject step. The accept-reject step is somewhat computationally intensive and also inherently stochastic. It's a random method. And the idea is to embed an optimization step in the algorithm I showed you before, the one that basically taking the accept-reject step, doing the exact same thing, but basically saying instead of the accept-reject step, I'm going to deliberately generate these fake pseudo-study replicates via an optimization optimization step that provides me a recipe for how to generate the electrodes, the fake electrodes. So here's kind of what I came up with and what I've been working on recently. The objective function is just a classic minimization problem. And what I'm doing, and I'll try and provide some intuition for this in a second, what I'm doing is I'm saying, here are the inflection points of this target electrode, the red one, let's say. And I'm saying to the accept-rejects, I'm saying to the integer program, give me the recipe for a fake electrode such that the distance, this distance, is minimized. And the reason why it's an integer program and not convex or some of the other powerful optimization steps is that in an attempt to enforce the constraints imposed by the resampling scheme that I told you about, the size, the proportion of observations that are subsampled from each electrode is going to come in these discrete sizes, just as we saw before with like the bag size. So that's why it's an integer program. It's forced to be. It's the solution space, the feasible set, is discrete. It's not convex. Okay, so let's try and get a little intuition for this. So here's a silly toy story, and the toy story I call the unlucky bartender. So the story is as follows: a bartender is asked, he's given a job, and he's asked to make a drink, and the boss says, "Look, you got to make this drink. We're making kind of a pitcher for some people. I want a 14-ounce mixed drink." But he's unlucky because the boss goes to the store that day and they're all out of liquor except for these silly little 1-ounce guys you get on airplanes and hotels and such. And so he comes to him and he says, "Look, we're low on liquor. You gotta use when you're making these drinks, you got to use only these 1 ounce things. You can't do like kind of smaller proportion. You couldn't do half of one, for example, half a shot or a third of a shot. And what's more unusual about this is he wants the alcohol content. The boss says, look, our customer says they want a drink that's exactly 31% alcohol, or as close as possible to it. And so, he's got some Baileys, vodka, wine. No one said it had to taste good, but the idea is that he's kind of stuck with these funny constraints, right? So how can we choose 14 of these silly little single shot bottles, potentially different ones, maybe they'll be the same, or some of them will be the same, such that we're as close as possible to 31% alcohol content. So we're minimizing this distance between the alcohol content that we want and the alcohol content of our mixed drink, right? And so I'm minimizing with respect to W, and W is basically a recipe that says, pour in 1 shot of vodka, 3 of Baileys, et cetera, right? And I'm saying, look, you can only pour in 1 shot at a time. I'm not letting you do a half a shot, a quarter of a shot, right? So each element of this vector, it can only be 1 shot of Baileys, 2 shots of Baileys, 0 shots of Baileys. And at the end of the day, it's got to sum to 14. The customer says they want a 14-ounce drink. So our matrix here is actually, in this case, just a vector, but each element of the vector would be the percent alcohol content of the alcohol, and the weights. Each element is going to be the corresponding number of shots that you would pour in. So that's more or less what I'm doing in my program. Here, instead of their shots, it's proportions of electrodes that we're subsampling, right? So if I got 1/10, 3/10, it would be a 10% of electrode 1, 30% of electrode 2 that we're supposed to subsample in order to make an electrode that's going to be really close to the target electrode. So how to do? So here I tried it on all 15 electrodes, and I just said, give me a fake electrode that's as close as possible to this one. So the solid line is the optimized one, and the dotted one is the target electrode. So the dotted one is the average CV of the target electrode, and the solid one is the average CV of the fake electrode that was subsampled from the constituent training electrodes. I've shown here the best case scenario and just kind of quartiles, just so you can get a sense for how well it did in general. It looks like, for the most part, they're close to indistinguishable. The worst case scenario, you do see some deviation, but this is not a reflection of the kind of integer programming, the optimization's abilities. It's just the fact that we have some electrodes are kind of outliers and look very different than the rest, and so there's only so much you can do in terms of making a fake electrode that looks like it. So the idea is to iteratively apply this integer program with different kind of distances, such that we're kind of getting variability in our ensemble. In each case, right, we fit this optimization step, so the I step of our fake electrodes in our ensemble. I fit this for some value of D, and I get back a script that says, okay, go ahead and make this type of electrode, right? And then I generate that fake electrode and I train a model just as we've been doing before. So it's identical to the accept reject step, but instead of accepting and rejecting randomly, I'm applying this. So here I'm showing just the raw and the derivative at different sample sizes so we can see how this scales, because one of the big kind of victories of this application is really the runtime. So at least in the raw, you can see that here I have the merged approach, which is the standard method, accept reject, and the integer program. The integer program is doing on par or a little bit better in some cases than the accept reject step and the merged, although there's some variability. It's not like these are enormous gains, but and then in the derivative case, we see that they're kind of all similar. The merged might even be a little bit better in some cases. But the big victory here is the kind of runtime. So if you look at the merged as the sample, so here on the x-axis I have sample size of each electrode. So if I had 15 electrodes, 2,500 means there was 25 observations from each electrode in my training set. And so kind of when we're using small amounts of observations, right? So remember before we had 21,000 observations per electrode. If we took maybe roughly, a little more than 1/10 of the observations and fit the merged, it does nicely. But very quickly, as you use more and more samples, the computation, the runtime just shoots up. And the accept reject step is actually surprisingly noticeably better, but the integer program does far, far better than it. Okay, so let's wrap things up. What did I talk to you guys about today? On my data set, when I properly tuned it, principal component regression produced superior predictive performance among some kind of subset of modeling schemes that I explored. Weighting, when we're in an ensembling setting, when we weight based upon the similarity in the CVs, we get some gains in terms of predictive performance. The best method, the ones we looked at, the covariate match study strap, gave us on average a 13.5, 3.75% improvements above that of the merged. You know, the 3.75% is admittedly fairly modest in the derivative, and so need more work to kind of improve upon the predictive performance in the derivative. We get a lot of computational efficiency with both the ensembling methods and the integer programming step, which can be important as we kind of continue to accumulate more and more training sets and have greater and greater data sizes or number of observations in each data set. But I'm also working right now on using the combinatorial methods to try and improve predictive performance. So, tying it back into the kind of greater neuroscience literature, there's a lot of limitations in terms of techniques that can be used to try and estimate neurochemical concentration with high temporal resolution. And so I think it's important to contribute in some way to the statistical methods that we use that kind of underlie successfully implementing these techniques. I also just think that playing around with some fancy methods also just kind of spoke to the robustness of kind of the standard methods that Dr. Montague and Kashida have been using. I think the gains in the predictive performance are modest, but provide a nice foundation for kind of moving forward. The computational efficiency gains could be really helpful as we kind of gain more and more data. I'm working right now on combinatorial optimization methods, kind of taking those further. I just showed you like kind of the very basic iteration of it. I'm also working with my group on kind of theoretical results regarding the statistical methods in general, not necessarily for this application. But I also, I'm in a biostatistics department, so my work is also focused on kind of generalizing these statistical methods. So I've been putting a fair bit of time into that. And eventually it would be good to try and quantify uncertainty of the underlying predictions. Big thanks to Dr. Montague for having me down, Dr. Ken Kashida and his group, who collected the data, my PI Giovanni, postdoc with him in his lab where I worked with Prasad, and the members of Dr. Chair's lab who gave us some of the lectures that we used. So thanks so much. I'll take some questions. Yeah.
Great talk, first of all. I have a question about the covariate profile similarity weighting.
Sure.
Did you keep the same weighting from just the raw Loewinger, or did you recalculate for the actual derivatives?
That's a great question. Yeah, so the question is, in the case where we applied covariate profile similarity weighting on the derivative, the numerical estimation of the derivative of the CV, did we calculate this similarity measure based upon the raw CVs, or did we calculate the similarity measure based upon taking the derivative of both of them? That's the question? Yeah, that's a great question. So on the raw. Where is it? I think it is a great idea to try it on the derivative. I've tried it on the derivative for the integer program, the combinatorial methods, trying to minimize the distance just between the derivative of the CVs. I've not tried it on the, I've not tried it looking at the similarity metric based upon the derivative, partially because I also was just uncertain. I'm just kind of flipping through randomly at this point. Here we go. I was uncertain if the kind of simple algorithm I'd use to find those inflection points, how it would do with the derivative, since the derivative kind of it can be a little bit shakier. But it's a great idea, and I mean, I think that your intuition about kind of just using the derivatives to evaluate similarity in the electrodes, I think is really good, and may end up being better. That's a good question. I've only, in terms of the covariate profile similarity weighting step, I've only done it on these. I haven't done it on the entire CV, although I suspect it would do well, if not potentially better. It's a good question. Like I mentioned, I've kind of minimized the distance with the integer program between the derivatives, the entire, all 999 points or what have you, but never in this weighting step.
So this notion of, okay, so I have two, maybe they're comments. Comment one is, so the inflection points, if you want to use, okay, so the idea is I'm going to take these electrodes, these different machines making the same kind of measurement. I'm going to either use them as a kind of basis set, or I'm going to cut them into pieces, use pieces as a basis set, and then generate data or project onto that, right? I mean, that's the shtick here.
Right.
Okay. So one inflection point, which is completely uninformative, is the one right there. That's due simply to the forcing function reverse change.
Right.
So it's not going to carry any information regarding anything but maybe something about the electrical characteristics of that electrode, but not electrical characteristics that we know are modulated by reaction with a modulator.
Sure, sure.
So in a sense, it's when I saw this, it's like this is you're fitting this, and you have this one thing hanging on to you. So
Yeah.
You've got to be close in an L2 sense
Right.
because of the inflection point, which is as meaningless as anything can be
I see. So you're saying it's kind of like a bit of a red herring for the methods.
for the method. So
Yeah.
I tried to decide, and I have an intuition for how it might be distracting the method. So for example,
Can I sort of follow up on that though? Because in some sense, for exactly the same reason, you could say is that's should tell you something about the pure electrical characteristics of the electrode.
it's pretty sharp acceleration of voltage. So you get this spectrum response to the whole. I mean, do we really care about that? If you did that, the fact is, we know that you can take this thing and randomly sample it. So I'm not surprised at all that your generation, that you can. So that was a good talk.
Thanks. Criticize. Please go ahead. That's what I'm here for.
What I'm saying is, what kind of got missed was, wouldn't it be great if we had gone after a signal routing on top of it? Well, I mean, you just did one thing, right?
Yep. Yeah, that's right.
Do we see anything where you showed any changes with regard to how well it was doing predictions?
So let's see.
This is how well does the ensemble method capture the sort of target function?
So sorry. Can you repeat the question?
He wanted to know, he wants to see how the different methods affect the prediction factors.
Oh, okay. Yes. You're talking about like how well it predicts concentration? Sorry, I must have been very, very unclear. All of these box plots are the RMSC of predicting dopamine.
Yeah, but that's just dopamine.
Just dopamine, that's right. Yeah, what Ken and I discussed this early on about, what the best way forward was. And we thought, keep it simple in the beginning, don't get too distracted, and then kind of try and apply it.
Yeah, this is a fantastic start. We would love to have a generative model of the electron. And this is a kind of parallel, this is like that, not quite that, where you could just extract a couple of parameters from the electron. And you go, oh, this is a such and such, generate a whole bunch of data from it, and then paste on top of that some sort of whatever.
Sure, sure.
But as we were talking today at lunch, I just kept thinking, we don't really know exactly what the heck is driving all these methods. We just know there's a lot of information there about concentrations on this that seem to just sort of override whatever it is that this cycling may do. So the red herring is
Well, can I offer a counter comment to that? Just think about so that inflection point. I think I totally agree with you. Based on what we've seen, that doesn't give you a whole lot of information about the chemical species of the identity, but it's this kind of electrical characteristic of the electrode. And so one of the things you do see, if you remember,
but also saturate most samples. I mean,
yeah,
it's
that's
a
the point where
saturable
you can
point
that's right.
in the measurement method that generates the curve in the first place.
When you go from the flow cell to the tissue, that's one of the points that changes the most, right? So the part of the idea in discussing this with Gabe was to try and identify from the flow cell
Okay, that's a different issue. That is, does this electrode look the same fake when I'm generating with my ensembling method in the tissue? That's a separate issue.
That's right. It's separate. I think what's interesting here is that if you have, in this case where you have known results where you can test against the truth, it seems like you do get some improvement when you can match those kinds of characteristics. And once you match that characteristic, there's other information throughout the sweep that's much more informative, and it didn't show, I guess, what the model is discovering.
I guarantee you, he would get no different results if he threw out the middle point and the one at the end, and the one at the start. I would bet money on that. So, yeah, right, here we go.
I see. So you're saying do the same thing we're doing, but make this 8x1 vector a 4x1 vector where each element is just the coordinates of these. So you're,
Instead of computing inflection points, that's the question as a raw as a comparison. What if I just took 4 random points along here?
and then just said what's the distance between them?
Yeah, we're going to take 4 random points. Those are going to be the things I'm going to measure the L2 closeness with. How well does that do? I don't know.
So you're saying like
Why get distracted by the inflection points?
I,
Was that a guess?
It was just, I think it was kind of a pseudo-random way of picking a couple of points to match. That's the idea. So I think that's
So does anything, are we surprised by anything here? Wait, where does pH, this is the dopamine, the average dopamine estimate, averaged over the pH levels.
that's right, exactly. That's right. Yep.
Can I ask just one? If you go
Sure.
to the box plot,
Yeah, which one? Oh, okay. Here we go.
like, what's the RMSE on the electrode itself?
Oh, you're talking about within electrode? It's much better.
Like, how much is much better? I'm just curious, like, how good these ones are relative.
You're talking about within an electrode? I would say it's probably about twice as bad.
For 500.
So I would say, so if we looked at, so let's just take a look at, let's look at one that merged, like kind of zooms in here. So we're doing in the 350, 400 range for these methods. What I found was that within electrode, the predicted performance varied considerably by the types of modeling scheme used. So for example, I tried things like random forests and these kind of more computationally intensive machine learning methods, and I could get predictive performance like RMSEs of like 20 and 30 within an electrode. But the problem is that, in my opinion, it's a fairly meaningless metric. And the reason why is because when I took random forest and I applied it to other electrodes, I mean, the predictive performance was horrendous. So it was massively overfitting to the electrode. So even slight perturbations were horrible, even when you applied any of these methods like merging or any of the ensembling stuff. And so I've kind of shied away from putting too much stock into how well they do. I will say that PCR, principal component regression, lasso, they tended to, at least in these methods, tended to perform kind of comparably in the like 200 range, 150 to 200.
What's your actual range of concentrations that you're putting over?
So it's,
If you were to look at this, these box plots are showing that you're systematically overestimating.
so let's see, systematically overestimating. What's your intuition about why it's systematically overestimating based on the box plots?
Show the box plots.
That count plot.
So we don't know. So when you show a plot like this, you don't.
Sure.
Experts. At least by a comment on time.
Yeah. Go. Oh, sorry. We're on the slide. Just show all of them.
This, go forward. You're talking about ones where we just have all of them?
4, 5.
Yeah, sure. Here, like this? Yeah.
That's where you were. So if you look, what is the middle bar? The median,
Yep, that's right.
right? And if you look at where your dots are, those are the outliers.
Uh-huh.
Those are all high. Which is fine. I'm just, if you showed a scatter plot, it would show us that probably more clearly. And I don't know your range of concentration, so it's like 2
2000 is very, very bad.
And what's physiologically the right range?
Yeah, so we did,
So nobody knows the last thing. I don't think anybody knows for sure the last thing. Do you? No. So I mean,
Well, so I mean, we're looking at, this is the RMSE, so these outliers are suspecting these like single points in bubbles or something.
uh-huh,
Right? These really big magnitude errors.
right, that's right.
But I think Stephen's question is, why don't we see any, like, why, so the plot seems to be biased towards a larger magnitude
Sure.
of the median. So if you're kind of, so, I mean, is that what you're looking at?
That's partially it. And then I'm trying to get a feel, like, we're dancing around a little bit what the noise is.
Sure.
And you mentioned just like in a half sentence, the derivatives being a little tricky. So how are you calculating the derivative? What's the noise level?
Sure, sure.
How are you a lot of what you're doing depends on derivatives potentially. Including these inflection points.
So when you say you think that the methods are overestimating, you mean that you think the predicted concentrations are much higher than the true concentrations? Is that what you mean?
The true is 1,000, and it looks like you're gonna, on average, predict 50.
Sorry, can you repeat your intuition for that? So because from here, since there's RMSE, I mean, all we know is that.
Oh, yeah, actually, I don't know. I don't know, but you're skewed, right? You're not.
Yeah. So I mean, I think the reason it's skewed is because there's a bit of a floor in terms of how well we can predict, but.
I guess all I'm saying is it would be really helpful to see a scatter plot of actual voltage or actual concentration.
I see what you're saying.
True concentration, because then you would see if there were systematic biases.
Sure, sure.
RMSE reduces it to like one number. I don't know how to say it more clearly than that.
No. Now I understand what you're saying. Yeah. So you're saying looking at specific concentrations, the comparison between the predicted and the actual concentration. Yeah. That would be a useful plot. In the future, I'll include something like that.
Yeah, I don't know if 1,000 is good or bad.
Yeah, it's quite bad here. Yeah, and to answer the question about the concentration ranges, we did. I can kind of back up.
actually, they're all kind of bad.
Yeah. None of them are great.
All those means are bad compared to what we got when we averaged it down over 100, 150 as opposed to 1,000. Well, I think it's because I think one thing which is hinky, is that a technical term in Boston? You go to the one with the red and blue, so I can just show this.
Sure.
So one thing is picking the four. Well, we know what points you pick, right?
Yep.
The peak and the curve part. Nobody really knows what that sag is. There is something happening on the surface of the electrode, like this sag. So after you have this initial.
Uh huh.
But are the traces
You're looking at the red electrode.
Or any of them, they all have little sags.
are the traces this
Yeah,
clean?
that's never been explained. But by only using 4
They're
points,
averaged.
Right, so I could see a derivative on this, but I can't, if it's very noisy, how are you calculating? Are you doing like a one back difference?
We're doing so. All of the derivatives, the comparison, the similarity measures are always on the average of the CVs. So we're averaging across all observations in it. So 20,000 or something like that. But you're right that taking the derivative on a single observation would not be informative. Yeah, we have to marginalize in a sense across the observations because the method is inherently combining a bunch of different electrodes. And so, we have to kind of have an average fake CV.
only having 4 points to bundles to generate this data potentially kind of encumbering in a way that's hard to see through anyway. Because when did you guys do this?
Year-ish. Up a year ago.
A year ago. Okay, so you can subsample this at random.
Right.
Like you can ignore the electrode. You can subsample. It's quite effective on the derivative. the derivative makes my point about the transients when you start, when you finish, and when you make a transition, just don't carry information. They're just not carrying information about. I don't know the degree to which you need information about the electrode.
So I think one of the results here is that if you have training data sets,
And I'm not sure I can make that decision based on this sort of ensembling scheme. And so maybe, why did you guys pick 4 spots?
it was
Just
one way.
start somewhere.
Yeah, that's right.
So I mean, one question I had was, if you reduce the number or increase the number, would you get a better match? So this is not, we're not training the model on what it was, right? This is just to get the match.
This is the way you ensemble the electrons.
Yeah, so
How do you generate data?
It's just the way we're kind of, it's just a similarity measure. I will note that I've done, to this point,
On all the points?
I have.
Take the L2 across the whole.
Yeah, I have. And it works, in some cases it worked a little bit worse, but it was generally comparable. In fact, I used it in the, where is it? There's a problem with having too many slides. Here, I used it in the optimization step, where this matrix, instead of each element being the vector of coordinates of the inflection points, I just used the entire average CV, and the performance was almost identical. So I think that at least in terms of using this step to minimize the L2 norm as a way of saying which electrodes are similar to each other, I think that there's a lot of reason to believe that the 4 inflection points is good enough, but if one was more comfortable with using the entire CV, it would be an identical methodology, it would just be changing the definition.
I now have a precise comment. So it's my sense that, so I understand what we're doing here. We're trying to match there are all these things that go into the electrical features of the response of this system that you built, a wire and a solar panel and all that kind of stuff. And then we expose it to things that differentially react on it and cause these oddball kind of wiggles in it. The sag being one of them. I mean, nobody's ever explained the sag. Why they concentrate on the oxidation point? Like why does the current sag? Well, the resistance is changing, right? That's the only possibility. And unless you think something's happening to the silver paint and the connector at the thing, so it's not. Okay, but really the thing that you want the similarity to is what context is this? What's really oxidizing? What's happening at the electrode, right? So I'm not so sure that's just an electrical system question.
Well, so part of the intuition that drove this was that the big changes you see between, say, the red and the blue, those are you see those just across electrodes, right? Just manufacturing electrodes before you show any chemicals to it at all. You just have it in a salt solution. You have these big differences from electrode to electrode. And if you have a simple situation where it's just open pH and you don't account for those differences, then the models produce worse outcomes when you go into.
Yeah, that's why I didn't see much improvement with the derivative. You couldn't really improve the derivative by
Yeah.
fancy energy programming schemes.
Right.
Because what the derivative does is smash that. So the derivative says, oh, we don't want to get in all this business of accidentally comparing humps in the raw space. We'll just get rid of all the humps.
So that was actually kind of surprising that it didn't also improve the derivative part of that. Like, I thought that doing this kind of summary matching would also improve in the derivative space, but the fact that it doesn't very much.
Because it's flat, pretty flat. The concentration dependent response is pretty darn. Can you go to one of the derivatives in it?
Yeah, sure.
What seems to be the derivative seems to be captured.
So sorry, you guys. We're now in the weeds. This is officially known as the weeds.
Let's see where.
I'd like to let's thank the speaker again. Thanks for coming.
Thanks for coming, everybody.